So from this point of view, amenable groups are boring, they've all got cost 1. We're interested in non-amenable groups, which actually turn out to have higher costs. You can have fixed price groups if the cost of gamma is equal to cost of E so that means that you can't actually the inf is attained by, in fact, every free action of G. And in fact, there's a question that's unresolved. What if gamma is a subgroup of delta of index n, then the cost of gamma minus 1 is n times the cost of delta minus 1. So using these kinds of properties, then you can actually calculate costs of quite a lot of groups. So the one we've all been waiting for, which probably attracted the most notice from this paper, was that the cost of the free group on D generators is equal to D. And so that implies if D is not equal to D primed, then no free action of FD with finite invariant measure is equivalent to any free So this is a really strong sort of separation between the possibilities for actions of the free group. And so this theorem, I mean, you could say it's an analog of the theorem of Sinai about entropies separating between shifts. I mean, that's a kind of analogous. It's a good invariant anyway. It does enable us to really think about amenable group action. And just to the cost of SL2Z is 1 1/12. Anyway, you can have a lot of fun with costs, and this is only a small indication of what you can do with them. But I think it's a very interesting new invariant that's come up just in the last 10 years kind of thing for analysing group actions. And certainly when Michael and I found out about it, we ran a seminar series on this at UNSW. There are some rather nice lecture notes on it. from, my mind's gone blank, often happens. From Kakris from UCLA. They're very readable, and they give a nice summary of all this stuff I've been talking about in this section of the lecture. So I don't think there's a very well-developed theory of costs for non-singular actions as distinct from measure-preserving actions. And I don't think that there's a good theory of costs for anything except countable groups at the moment, but it would be quite interesting to try to extend it into both those domains, I think. There are some, you can work out if you know what amalgamated free products. In fact, I might as well do a commercial for some of my work with Goladets, where we we worked out the costs of various groups that are not just the free group. But Kakris and Miller, thank you. So the last thing I was going to talk about was, are there some good invariants for semi-simple group actions? And my colleague Michael Cowling, together with Hargrup and people, found some quite interesting invariants for semi-simple actions, which enable you also to distinguish between actions of semi-simple groups. And I thought that might be a good topic to finish this series of lectures on. So we've seen that ergodic theory is about trying to find projections onto the invariant set. So we need to think about the identity representation in the dual of a Lie group and how that can be approached by other representations. At least this was the... So if pi is a represent... So I guess that G is now going to be semi-simple Lie. Oh no, maybe it's not. Actually, I'll talk about. So take a group G, and a representation in a Hilbert space H. Almost invariant vectors if you can find a sequence psi n in H of vectors of length norm 1, so that as n goes to infinity, these things become almost invariant, uniformly on compact sets. In fact, this says that if you've studied Mackey-induced representations and things like I did when I was a young man, this says that the trivial representation 1 is weakly contained. And this is equivalent to saying do I believe this? Yeah, I do. So we say that pi has a spectral gap if the opposite holds. If there exists a probability measure whose support, I think I needed, support generates all of G with pi mu strictly less than 1. So these are two kind of opposite extremes in the sense that it was proved by Becker, de la Harpe, Valette, all that team, that a unitary representation of G has almost invariant vectors if and only if it does not have a spectral gap. And G is amenable if and only if L2 of G that's almost one of the sort of known equivalent definitions of amenability, really. At the opposite end of the spectrum, sorry, there's no spectral theory involved in that remark at all. A group has so Kazhdan's property T, which you read a lot about, may be formulated to say every continuous unitary representation without an invariant vector has a spectral gap. which is saying that pi is an isolated point. So 1 is the identity is an isolated point in the unitary dual is another way of saying that. Now, it's known that this is that groups with a spectral gap, their actions can't be equivalent to actions of groups without a spectral gap. So, in fact, we can say a little bit more than that. We can say that in a more precise way. Well, in fact, there's some nice properties. How am I going? 15 minutes. Supposing we have a locally compact group with property T. Mu an absolute continuous symmetric probability measure whose support generates G. Then there exists a constant delta less than 1, so that independent of mu, pi mu is less than delta for all unitaries with no invariant vector. So that's a reasonably strong statement about how big the Fourier transform of a probability measure can be. It's actually bounded away from 1 unless there's an invariant vector there. And so, using this Amos-Nevo, if G is connected semi-simple Lie group, let's suppose we've got an action of G on X mu which has a spectral gap. That means that if you decompose that into well, no, the action of G on L2 of X mu is a representation with a spectral gap, then so this is the ergodic theorem I was talking about before for these things. You can actually estimate how far the pointwise limit of this thing is from the actual limit. where theta p only on P and the action. So remember we said that the speed of convergence here was something to do with entropy. That theta p there is saying that there's actually some kind of entropic condition about the speed of convergence there. So those are some recent theorems. Now, last but not least, let me talk a bit about, say a few words about the Cowling-Hagerup theorem. I have only 10 minutes to do that. Because that is another invariant that came up which is related to this spectral gap theory. So this is in the context now those of us that have been working on Heisenberg type groups and so forth remember that there are not so many of these. And the exceptional group F4, this F is not to be confused with the free group. These two guys are not property. Well, none of these. In both these cases, you can get to the trivial representation from within the unitary dual, but these two ones have property T. But nevertheless, what Michael and Uffe were able to prove was that you can approach representations, the trivial representation in these, not by unitary representations, but by uniformly bounded representations, which are nearly as good as unitary representations in some sense. So what they managed to do was define a constant called the Cowling-Hagerup constant, lambda g. So I'd like to try to define for you what lambda g is. This gave a new invariant which enabled you to distinguish between different actions of SPN1 and F4. Maybe I'll get a new piece of chalk. So if you take the space of matrix coefficients of the regular representations, then you get the Fourier algebra. Say M. So which functions multiply this span of the matrix coefficients into themselves by pointwise multiplication? We'll call those functions M. M is called completely bounded if so you need to take the dual of the space A of G, which is the von Neumann algebra of G, so I'll note its norm in the von Neumann algebra as M naught, and the proposition that makes us sit up and take notice is G is amenable if and only if there exists a net Mi, I and I of functions A of G with what are they called? UI. I'll call them UI. So it's an approximate identity with norm bounded by 1. Here ui times v approaches v. It's like saying there's an invariant mean on L infinity. It's a slight change of that. So let's change that definition just a little bit. Let's change that definition just a little bit. So let's supposing we have a group where you can find an approximate identity whose M naught norms are bounded uniformly by L. We'll let lambda G equal to be the infimum of L if such a net exists, and equal to infinity otherwise if you can't find such a net. So this is the Cowling-Hagerup constant, and this is a constant that enables you to distinguish between actions of the symplectic group and F4. So for then